Atmospheric air is not a single, uniform gas. It is a dynamic binary mixture composed of dry air, mostly nitrogen and oxygen, and water vapor. Conditioning this air inside a building, whether heating, cooling, or dehumidifying it, requires tracking the internal energy of those moving molecules, as well as shifting partial pressures as the water vapor undergoes phase changes. Historically, this posed a major engineering bottleneck. Before graphical tools existed, tracking a system's state meant solving dense, interconnected, non-linear equations derived from first principles for every single degree of temperature change. The engineering solution to bypass that mathematical grind is the psychrometric chart. This chart takes the axioms of thermodynamics and the Gibbs-Dalton laws of partial pressures and maps them into a single, two-dimensional vector space. It acts as a geometric solver. Instead of performing raw calculus to calculate the energy required for an HVAC system, engineers plot coordinates and draw vectors to define complex phase changes. To lock down the exact physical state of a mixture, thermodynamic laws dictate we must define exactly two independent properties. This horizontal axis represents dry bulb temperature. It tracks simple, sensible heat, the ambient temperature read on a standard thermometer, uninfluenced by the amount of moisture in the air. We cross that with a vertical axis, the humidity ratio, designated as W. This is a measurement of mass. It defines the exact weight of water vapor mixed into 1 pound of dry air. The ratio is governed by the Gibbs-Dalton law of partial pressures. The numerator isolates the partial pressure of the water vapor, while the denominator strips that vapor pressure away from the total pressure to leave only the value of the dry air. Plotting a specific temperature against a specific moisture mass yields a single coordinate point on this grid. That point locks in the precise physical state of our mixture. It becomes our anchor. By graphically isolating sensible heat on the x-axis from latent mass on the y-axis, we establish the coordinate foundation for psychrometrics. Water vapor has a maximum physical capacity in air, which is strictly dictated by the mixture's temperature and pressure. Look at this sweeping exponential curve capping the far left of the grid. This is the saturation curve. It defines the state of neutral equilibrium between the moist air and condensed liquid water. This curve acts as the absolute physical boundary of the chart. Thermodynamic states cannot exist to the left of this line. When we cool our air mixture without removing any of its moisture, the point tracks horizontally to the left until it collides directly with the curve. The exact temperature where that horizontal path intersects the boundary is the dew point temperature. Because the air has hit its maximum capacity, any further cooling drops the temperature below the dew point, forcing water vapor to condense out of the air as a liquid. The saturation curve translates abstract equations of vapor capacity into a physical wall, dictating exactly when and where condensation will occur inside an HVAC system. To obey the first law of thermodynamics, engineers must track the total energy flowing through an open, steady-state system. We quantify this using specific enthalpy. Enthalpy combines the internal energy of the molecules with the flow work required to push the fluid across a system boundary. These oblique parallel lines cutting across the chart represent total enthalpy. The value is calculated by summing the individual partial enthalpies of the dry air and the water vapor. By mapping these diagonal isolines, the chart allows engineers to instantly read total system energy without calculating internal energy and pressure volume work separately. Enthalpy operates alongside the finely dynamic wet bulb temperature. While enthalpy measures total energy, wet bulb measures simultaneous heat and mass transfer. This diagram illustrates an adiabatic saturator. As liquid water is sprayed into an airstream, it evaporates. That evaporation cools the air until the mixture reaches full saturation at a constant pressure. The equilibrium temperature the injected water eventually reaches is defined as the wet bulb temperature. On the chart, wet bulb lines originate at the saturation curve and project diagonally downward. They look nearly identical to enthalpy lines, but they diverge slightly because wet bulb lines must explicitly account for the sensible heat added by the moisture evaporating into the air. By layering these diagonals onto the coordinate space, the chart integrates total energy and the absolute limits of evaporative cooling directly into the temperature mass grid. To accurately size fans and ductwork, we need one final property: specific volume. This is the physical space occupied by a unit mass of dry air. These steep, nearly vertical lines across the grid plot the specific volume. This property is derived directly from the ideal gas law for the binary mixture. Look at the P sitting in the denominator of this equation. That represents the total barometric pressure of the surrounding environment. As altitude increases, total barometric pressure drops. Because pressure dictates the denominator, dropping atmospheric pressure forces the specific volume of air to expand. This physical reality invalidates standard sea level charts at high elevations. To maintain mathematical accuracy, ASHRAE publishes entirely separate charts calibrated specifically for altitudes of 5,000 and 7,500 feet. The specific volume lines anchor this two-dimensional chart in physical three-dimensional space, forcing the mathematical model to account for geographic altitude and atmospheric density. We have deconstructed the static properties. Now we apply them dynamically. In this fully populated state, real-world HVAC processes are simply geometric vectors drawn between equilibrium states on the map. We start at an initial state, for example, a hot, humid room requiring conditioning. Sensible cooling is a pure temperature drop. It removes heat without changing the moisture content of the air. On the chart, this translates to pure horizontal movement to the left. Dehumidification removes moisture mass without altering the dry bulb temperature. This plots as a pure vertical drop downwards on the y-axis. Since an actual cooling coil performs both simultaneously, it generates a single diagonal vector, pointing down and left, directly toward the final conditioned state. The psychrometric chart provides a unified visual framework for thermodynamic analysis, condensing the first law, Dalton's mixture laws, and complex phase changes into actionable geometry.